Hello, welcome to part 4 of AQA 2018 Physics Paper 2. So talking about the angle of reflection in this experiment before. So plane mirror ray box reflected ray. So angle of incidence and angle of reflection in a table. So it says for each angle of incidence, the angle of reflection has caused a range of values. This is caused by an error. So what type of error would have caused each angle of reflection to have a range of values? So yeah, writing human error is not quite, it's actually called random error because it can go either way. If it's always the same error each time, it's called systematic error. That's usually a problem with the equipment that you're using. But random error usually is caused by humans or some other external factor like the equipment. Okay. Suggest what the student may have done during the investigation to cause each angle of reflection to have a range of values. So if it's random, they might have done the same thing each time. We can put some suggestions. Okay, so I'm going to write underneath here. So they might have misjudged the center of the ray. Okay, not putting ray box to the same position. So anything, only one mark, anything sort of sensible. Probably yeah, just misjudging where the ray is really. Okay. Estimate the uncertainty in the angle of reflection when the angle of incidence is 50 degrees. Show how you determine your estimate. Okay, so let's have a look at the other measurements. Okay, so S1, 56. Oh, it goes from the range there is 10 degrees. It's got a lot, isn't it? 56 to 46. Let's write that down. So we can paste this in. Bear with me. Uncertainty. Apologies, just put this back. Bear with me. So yes, 10 degrees is the range. I'll put that in so I can write in it. Right, sorry about this. Just quickly get back. Right, so I'm going to write this answer here. So 5.3. And so the range. That's a question I'm answering here. So estimate certainty. The range is equal to 10. And we want the uncertainty is the mean. Let's look at one. So the uncertainty is the mean. So it's 5 degrees each side. Okay, 5 degrees each side. So 5.4, the student concluded that a plane mirror, so that for a plane mirror, the angle of incidence is equal to the angle of reflection. Explain why you agree with this conclusion. Use examples from table 2 for your answer. So I'm going to write 5.4. Okay. I'll write that underneath that one. Apologies for this, it's kind of getting a little bit haywire, but we'll get there. Right, so equals. So yeah, good experimental accuracy of 5 degrees each side. So the angle of incidence, I think it's 80 marks, is equal to the angle of reflection within experimental certainty for all results. Okay, so I'll use examples from the example from the table. So I'll use some examples. Okay, so test 1. So for 20 degrees, the angles of reflection, what was the actual max was a range there, so it was maximum 2 degrees out. Okay, so what extra evidence could be collected to support the student's conclusion? What extra evidence? So you could say expand the range of angles measured. So under 20 degrees and above 50 degrees, wasn't it? Above 50 degrees. 1 mark. Okay, that's a 1 mark thing. So state 1 change a student should make to the apparatus if he wants to use the same method to investigate diffuse reflection. Okay, so we've got specular there, it's plane mirror. So use an irregular reflective surface instead of a plane mirror. So it's not going to get the same results at all. It's irregular. Okay, number 6, moving on. Figure 8 shows a boat floating on the sea. Okay, boat is stationary, it's not moving. Figure 9 shows part of the free boat diagram for the boat. Okay, the free boat diagram for the boat. So complete the free body diagram for the boat. So we could just draw it on here. Okay, there's okay, we'll just draw it on the boat. There's some pre-drawn things that where the boat sits. So arrow, so we've got 2 forces. Actually, we could just put an arrow in, can't we? So we've got backwards force. So we're going to do to make that the same, I'm going to copy it. But they have to be in the exam, they have to be the same length, but just pointing different directions. So you measure it with a ruler. Okay, so the upwards arrow. Okay, so that's up thrust. Downwards is gravity or weight. I'm going to go for weight there. Okay, weight incorporates that. So it says calculate the mass of the boat. Use the information in figure 9. Gravitational field strength is 9.8 newtons per kilogram. Okay, so there's a separate paper. Let me just bring this up for 2 seconds. Okay, just while I bring this one up. Question 9 had a diagram in it. Let's just copy and paste it over. Bear with me for 1 second. So yeah, it's not copy and pasted correctly into the word. Right, so I'll bring it up for you here. Okay, so yeah, it doesn't look like it's part of that question, does it? So we've got to be careful with that in the exam. So scale 1 centimetre is 5 kilonewtons. Okay, so you have to measure that out in actual. So it's actually a to scale diagram. Sometimes you'll get that in the exam. You'll get diagrams actually to scale. Okay, so let's look at the measurement of it. Okay, and I'm just going to measure this. For a moment. Just take it off. So 1 centimetre, so we've got 1, 2, 3, 4. Right, so that is, so it's 5, so 5 times 5. Okay, so that's 5 centimetres. Yeah, so you have to actually get a ruler and actually measure that in an exam. Okay, so let's write this down. So weight is 25 kilonewtons. Okay, just calculate the mass. Okay, it's easy enough, isn't it? So once we've measured that, okay, that's the weight. So now we just divide it. So it's 25,000. Okay, so what we need to do is divide that by 9.8. Okay, and that will give us the weight. If you remember that weight is mass times gravitational field strength. Yeah, it's a bit of a funny question, that one. Because it had a diagram which didn't look like it was part of the actual question. Because it was like further down the page. Just actually had to look like it in the actual paper. Okay, so when the boat propeller pushes water backwards, the boat moves forwards. The water in the boat causes an equal and opposite force to act on the boat, which law is an example of. So it's Newton's third law. Equal and opposite reactions. So if you remember the first law, that is, an object doesn't move unless there's a resultant force. F equals ma is acceleration is proportional to force applied. And Newton's third law is equal and opposite reactions. Bit of a summary. Okay, so oops, got a bit of an error. Let me just get rid of that for you. Okay, so figure 10 shows the boat. Okay. Figure 10 shows a boat towing a small dinghy. That's a dinghy, that's a boat towing it. The tension force in a tow rope causes causes a horizontal force forwards and a vertical force upwards on the dinghy. So set with an angle. Got horizontal force forwards 150, vertical 50. So the horizontal is a lot bigger. Okay, so next question. Figure 11 shows a grid. Again, this is from the actual paper. Show you. No, it doesn't really help that much with the actual question. Just get it up. So what it is it's squared paper. Okay, like this, it's squared paper. So draw a vector diagram to determine the magnitude, so the resultant, of the tension force in a tow rope and the direction of force caused by this on the dinghy. So I'm going to sort of draw it freehandish. Okay, so you've got, again, it's all in words, it's quite, I'm going to draw it here. We've actually got the words. We used to have it there, wouldn't it? So it really makes sense where they put it there. So 140, so let's draw it here where we see the words. Make it a bit easier while we're doing this. Horizontal force, 150. So you've got to draw it to scale. So example, you draw 15 centimeters long. Example, I'm going to make it a little bit longer. Okay. And then you have to draw 50 upwards. Okay. So that one's about 3 times longer than that one. Let's do it to scale. Okay, so the resultant resultant will be this. We have to measure the length. Okay, let's measure the length. So you would get marks in the range 156 to 160 newtons. Okay, so 15.6 centimeters to 16 centimeters long. Okay, it's all about drawing to scale. That one, I didn't tell you, but it is about drawing to scale. Okay, so again, all as well, you have to have a tractor to measure that angle. Okay, because yeah, this is when we draw. The magnitude is that length, that resultant length, kind of hypotenuse, and the direction is this here. So it's between 18 to 20 degrees from horizontal. So that one's actually a to scale drawing. Okay, number 7, completely different thing. So a student used a simple transformer to investigate how the number of turns on the secondary coil affects the potential difference across the secondary. Well, we know it does when we about transformers. The student kept the PD across the primary coil fixed at 2 volts. Figure 12 shows the results collected by the student. Potential difference across secondary, number of turns in secondary. So again, quite a linear relationship from before. Figure 12 shows one anomalous result. Handily, they've put a ring around it for us. Suggest one possible reason why the anomalous result occurred. Okay, so let's give you a few reasons for this. We're not allowed to write human error this time. So you could put too few, because yes, it's for one result, isn't it? So there's not an error each side. Too few turns or coils secondary, or PD across primary was produced. Okay. Transformer changes from being a step down to a step up transformer. How can you tell from figure 12 that this happens? We step down. Let's have a look. Potential difference coil in volts. Number of turns secondary coil. Let's have a look. Oh, not passed. So what happens there is the PD across the secondary coil is higher than the PD across the secondary across the primary. Yeah, it's quite a tricky one, sorry. After 20 turns. Number of turns secondary. Secondary, number of turns secondary. Yeah, we've got to go back to here. It's got student kept the primary coil fixed at 2 volts. So it goes there. You have to read that bit. It doesn't look like it's irrelevant again. This is how it's spaced out in the exam, but it's because it goes above the point. It goes above 2 volts. Become a step-up transformer. Okay, a spot welder is a device that uses a transformer to produce a large current to join sheets of metal together. So figure 13 shows a transformer demonstrating how a large current can heat and join 2 nails together. Okay, so you've got variable AC. Remember, you need AC for a transformer. Coil with 640 turns, coil with 4 turns, power output and potential difference. So how does the amount of infrared radiation emitted by the nails change when the power supply turns on? So to get hotter, the infrared radiation increases. We have to write there because it increases. Okay, that's actually because they get hotter. Okay. So calculate the current from the power supply needed to provide a power output of 336 watts. Okay, so what I'm going to do is I'll do this in the next video. So thank you for listening, and we'll continue in part 5. With the part. Thank you, and I'll see you in the next video.